Alright, so let's be given this diagram of a guy being pushed to an equilibrium height on a swing due to a force. And the question asks you, what is the total work done by the 60 newtons applied force? To start, we need to know the work energy theorem applied to a curved motion. So if we have a particle going from P1 to P2 on this curved path, we can define dl as an infinitesimally small displacement vector, so it's just a small part of this path. And if we draw an arbitrary force being applied, during this infinitesimally small displacement path, the force will do a small amount of work, dw, on the particle, given by this equation here, where the small amount of work is equal to the force times the small displacement, which if we also remember, it's equal to FDL cos phi, where phi is the angle between the force and the path. You can also write it as F parallel times dl, where F parallel is just the force parallel to the direction of the path. We define our work equation for this motion, given by these three forms here, where P1 to P2 is the path of the object. F parallel is equal to F cos phi, and it's just the force parallel to the dl direction. dl is just a small part of the total path. We can apply this to our situation. However, we're going to have to apply a change of variables. During the path, we can define it as s, the total displacement. And if we take a small amount of this path, we can define this small path ds as approximately equal to the radius times d theta. And this is equal to dl. Plug this in for dl in our integral equation. Then we also have to identify our other variables. We can also apply the force equal to 60 newtons. But what is P1 and P2? Since we're changing to d theta, it's going to be the change in the angle. So it's going to go from 0 degrees to 30 degrees. So if we plug all these in, we still don't have cos phi. We have to remember that we converted our integral from dl to d theta. And our angle phi actually changes as theta changes. So it depends on theta. And so we're going to apply this approximation, which is actually not the correct approximation, but it's still the correct process. So we're going to say that phi is approximately equal to theta in this situation. If you remember phi is the angle between the force and the change in the path, and theta is the change between the vertical and the swing. So this approximation is not correct, but we're just going to use it for this example. You just change cos phi to cos theta, and then we can apply r equals 2 meters. That's the length of the swing. Do a simple multiplication, we get 120 joules. Do the integral of cos theta d theta. The integral of cos theta is equal to sine theta, and then we can apply the upper and lower bounds. Do sine 30 minus sine 0. Sine 0 is just equal to 0. Sine 30 is equal to 1/2. End up getting 60 joules for the final answer. This is the work to bring the swing to an equilibrium position, defined at theta equal 30 degrees. So this answer is assuming that at the angle 30 degrees, the swing's in equilibrium. And this just means this is that one position in the motion where the swing's at rest is changing from going up to down.